Hello. Hi. Uh, yeah, hi. Hello. I am 𝐒𝐲𝐫𝐿 Ghosh. I am a senior CPU design verification engineer currently working at Synopsys. I am working at Synopsys for the last more than 1 year. And previous to this, I have been working in Intel for more than 2 years, like 2 year, 4 months. And before that, I did my MTech from IIT Kanpur. Uh, and I was a topper there. And I have a deep passion for VLSI and digital design. So I started this. So this playlist is actually walkthrough for the HDLBit problem solving. And prior to this, I have solved multiple problems. And we'll in this part we'll be continuing with the next set of problems. Okay, whatever till whatever we have solved. From that we will continue. So I'll be sharing my screen. But uh, before you watch this walkthrough, try to solve the problems yourself. And if you have some doubts, then watch how I am solving it. Okay. You can also see how differently I'm solving it from you. And if you have a better approach to solve any of these problems, feel free to drop that in the comment section. If you have any doubts, please let us know. Because if that is a small doubt, we will solve it in the comment section. Otherwise, I'll make a separate video to clear that doubt. Okay. So yeah, first try the problem yourselves. And if you are stuck, see this walkthrough. Okay. So let's start with this combined circuits A and B. Okay. Let's see what this is about. So here it says see this Q4A and Q4B. Okay, I hope it's visible and audible. Okay, this Q4A and Q4B, these are the two modules, and they are connected like this. And the top level design consists of two instances, each of subcircuits A and B. So two instances of this circuit. So A, B, B. Okay, and they are connected like this. So we have to implement this circuit and write the code for this. So we have to write Z equal to what of X and Y. Okay. So what we will do is we will try to reduce this circuit. We will see what is the output of A and B are. Okay. So let me take a paint and let's see what is this actually. So Q4A says, so I can say here A equal to X XOR Y, okay, and X, which eventually means X bar Y plus X Y bar into X or AND of X. So if I just do AND of X bar and X, it cancels. So this term will cancel and we will be left with X Y bar. Okay. So A output says X Y bar. And what does B says is, okay, I shouldn't have done that. So this is the B problem. What it says is the output is 1 when X, Y both are zeros or X, Y both are ones. So it's like x bar y bar plus xy. Okay. The B output says it's x bar y bar plus xy. Okay. And what it is saying is we do OR of, okay, this A or B. So this output A or B, and then I do A and B. So this is A output and B. A and B. Okay. And then I do XOR operation of that. It's like A or B. Okay, let it be. What to do is A or B. So we will find this now. Okay. What does A or B means? So A is X, Y bar plus X bar, Y bar plus X, Y. X by Y bar plus X bar, Y bar plus XY. Okay. And XOR A and B. So if I do X, Y bar and with, okay, X bar, Y bar plus XY. Okay. So if I do X, Y bar and X bar, Y bar, so what happens is X and X bar create, like, cancels each other. Okay. So this term goes away. And then when I do X, Y bar with this, the Y bar and Y cancels these two terms. So this term goes away. So it's like X, Y bar. Okay. And with 0, which is equal to 0. Okay. So I am doing X, Y bar plus X bar, Y bar plus XY XOR with 0. Okay. Which means this is 1 0 plus 0 0 plus 1 1. Okay. So if I just draw K math, there are many ways to find this actually. So I'll do X and Y 0 1 0 1. So here I am saying it's 0 0, which is present, and then 1 1, which is this, and 1 0, which is like X is 1, Y is 0, which is this. So if I just do the math, I mean do the calculations, if I do the grouping, it's like Y bar plus X. Okay. X plus Y bar, anything is like fine. Okay. So that is the final output, which is equal to this final Z. Okay. So this is what we need to do. What we will do is we will say assign Z equal to X or with not of Y. X or Y bar. Okay. X or Y bar. So we don't need to give a bracket, but if you want, you can put a bracket here as well. But yeah, that's pretty much it. Uh, yeah, you see, it's a success. Very simple problem. It looks big, it's not. Trust me. Many of the problems seems difficult, seems complicated. Those are actually very simple ones. Okay. Okay, let's move on to the next problem. It says a ringer. Okay. So ring or vibrate. Suppose you are designing a circuit to control a cell phone's ringer. You are designing a circuit which will control the cell phone's ringing and vibration motor. Ring and vibration motor. Whenever the phone needs to ring from an incoming call, input ring, your circuit must turn on the ringer. Okay. Output ringer equal to 1. Or the motor, output motor equal to 1. Whenever your phone needs to ring from an incoming call, input ring, the circuit must turn on the ringer or the motor. Okay. But not both. So it should be either ringer or motor, not both. If the phone is in vibrate mode, input vibrate mode equal to 1, turn on the motor, otherwise turn on the ringer, but do not turn both. Try to use only assign statements to see whether you can translate a problem description into a collection of logic gates. Okay. Okay. Design hint. So let me see, input ring, input vibrate mode, output ringer, output motor. So whenever there is an input ring, okay, but not both. If the phone is in vibrate mode, if vibrate mode equal to 1, turn on vibration, turn on the motor, otherwise turn on the ringer. Okay. When vibrate mode equal to 1, so it's like assign motor equal to what we will assign to the motor. We will first check if there's a ring or not. So we will say ring. If ring is 1, okay, if ring is 1, okay, so we will check if ring is 1 and no, if ring is 1, then check. Okay, okay, okay. So what we can do is if ring is 1 and vibrate mode is 1, if ring is 1 and vibrate mode is 1, then give one tick B1 to the motor. Otherwise give one tick B0. Okay. Otherwise ringer equal to when ring is 1 and vibrate is 0, it's like not a vibrate. Okay. If ring is 1, if input ring is 1 and vibrate is 1, we assign 1 to the motor. We say vibrate, otherwise 0. And if ring is 1 and vibrate is 0, so it's like vibrate is not there. Then ring. If vibrate mode is there, we will turn on the motor. Otherwise, if vibrate mode is not there, we will turn on the ringer. Okay. So this will be the circuit. Anyways, before I submit, let me see what all things are there. Try to use only assign statement to see whether you can translate a problem description into a collection of logic gates. Design hint: when designing circuit, one often has to think of the problem backwards, starting from the outputs, then working backwards towards the input. Okay, so it's like a reverse engineering. This is often the opposite of how one would think about a sequential or imperative programming problem, where one would look at the inputs first, then decide on an action. This is opposite to one how would think about a uh, sequential or imperative programming problem. So this is unlike how we think of a sequential problem, where one would look at the inputs first, then decide what to do with it. Here we look at the output first and decide what to give at the input so that we get this output. For sequential programs, one would often think if inputs are this, then the output should be this. On the other hand, hardware designers often think the output should be this when inputs are this. I mean, the output should be this. In that case, we have to make inputs as this. The above problem description is written in an imperative form suitable for software programming. Ring, then do this. If you must convert it to a more declarative form suitable for hardware implementation, assign ring are equal to something. Being able to think in and translate between both styles. Being able to think in and translate between both styles. One of the most important skills needed for hardware design. Okay, anyway. So because there are two outputs, we cannot put them in one assign statement. We can actually. There is a way we can put them in one assign statement. We can say assign. We can concatenate motor, comma, ringer. So that also we can do. What we can do is, you know, what we can do? We can do assign motor, comma, ringer. Okay. And then we can put values. Okay. So I can say if ringer, if ring, okay. In that case, okay, check vibrate mode. Vibrate mode. So this is the first part of the. So if vibrate mode is there, we will say if ring. So when ring happens, so if vibrate mode is there, what we will do is we will say 10 to tick 10. Otherwise, if vibrate mode is not there, then we should ring. So it's like 2 tick 01, 2 tick 01. Okay. Otherwise, if ring itself is not there, what we will return is 2 tick b 00. Okay. So this will be another one way to solve it. So what we are giving to motor and ringer is if ring is there, then we will do this. Otherwise, we will return 0. If ring is not there itself, if there is no call coming, we will give 00. But if call is coming, we will check vibrate mode is there. If vibrate mode is there, we will return motor 1 vibrate, but don't ring. So it's like 10. Otherwise, return 01. So don't vibrate, only ring. Okay. So we will try this first. Let's submit and see what is the output. After that, okay, we will try out the this one. Okay. See, It's a success. So what now we can do is we will just comment these two and uncomment this. Okay. So this is a shortcut way to write the same thing. It's like a one-liner way. Okay. So now it's running again. Okay. There is two tick B. I don't know why I didn't wrote B. Uh, like very bad actually. Now see, it's a success. So it's the same way of writing this thing in one line. Okay. So yeah, this is pretty much it. So you can see this how I am writing, and okay, let's move on to the next problem. Okay, thermostat. It says a heating cooling thermostat. Okay, a heating cooling thermostat controls both a heater. Is a heating cooling thermostat controls both a heater during winter and an air conditioner during summer. There's a thermostat which can measure the temperature, and it can control both a heater and an air conditioner. So during the winter, it controls the heater. During the summer, it controls the air conditioner. Implement a circuit that will turn on and off the heater. You have to implement a circuit that will turn on and off the heater, air conditioning, and blower fan as appropriate. So there are a few things that will turn on and off the heater, air conditioning, and blower fan as appropriate. So what is the logic? The thermostat can be in one of the two modes: heating mode equal to 1 and cooling mode equal to 0. Okay. In heating mode, turn the heater on when it is too cold. In heating mode, turn the heater on when it is too cold, that is too cold equal to 1. But do not use the air conditioner. In heating mode, turn the heater on but do not use the air conditioner. In cooling mode, turn the air conditioner on when it is too hot but do not turn on the heater. So do not turn on the heater. When the heater or air conditioner are on, so it's like either heater or air conditioner are on, also turn on the fan to circulate the air. When the air conditioner or heater are on, turn on the fan to circulate the air. In addition, the user can also request the fan to turn on even if the heater and air conditioner are off. Okay. Try to use only assign statement to see wherever you can translate a problem description into a collection of logic gates. So it's like we have too cold, too hot, mode, and fan on. Okay. And we have heater, air conditioner, and fan. So when heater will be on, so we have to write three logic. Okay. Assign heater equal to, so when heater will be on, heater will be on when too hot is 1. Sorry, too cold. Heater will be on when too cold is 1, too cold, and not of too hot. So when too hot is not there. Okay. So it says Okay. In heating mode. So when mode equal to 1, when mode equal to 1. So we don't need to check too hot or not. When mode equal to 1, heating mode. Mode and so when to turn on the heater? Heating mode and cooling mode. In heater mode, heating mode, turn on the heater when it is too cold. When it is too cold. In heating mode, okay, when the mode is 1, when mode equal to 1 and too cold, when too cold, okay, then only turn on the heater. Then one tick B1, otherwise one tick B0. I don't need to check whether heating mode and too cold is 1. So these two I need to check. I don't need to check too hot is 1 or not. It can happen too hot and too cold both are 1 at the same time. So some random logic came, which is, I mean, which should not come ideally, but it can come because there can be a flaw somewhere. If mode is 1, then only we will check too cold or not. Okay. I'll say assign air conditioner, air con, okay, equal to when mode equal to 0. So when not of mode, okay, the complement of mode and too hot, then give air conditioner equal to 1, otherwise give 0. Okay. And these two are actually outputs, heater and air conditioner. But what we will do is when heater or air conditioner are on, turn on the fan to circulate the air. So assign fan equal to heater or air conditioner. So whenever there's a heater or air conditioner, okay, or when there's a request to turn on the fan, when fan on, okay, give one tick B1, otherwise, sorry, give one tick B0. Okay, you're getting this right. So what I am saying is when to turn on the heater, it says there's a thermostat which has two modes. So this mode can be 1 in heating mode. So heating mode means it's very cold actually. So mode can be 1 in heating mode. In heating mode, so when mode equal to 1, turn on the heater when it is too cold. So when mode equal to 1 and too cold, turn on the heater. Okay. Otherwise turn off the heater. For air conditioner, okay. Cold, but do not use the air conditioner. So we have to also write a logic. If that is the case, do not use the air conditioner. Okay. So what we can do is anyway, this also will, you know, uh, this logic will also work because if mode is 1, this becomes 0, the result becomes 0. If result becomes 0, output becomes 0. Air conditioner becomes 0. Do not use the air conditioner. Air conditioner will become 0. When mode is 1, even if too hot is there, then also air conditioner will be 0 because it is in heating mode. Okay. When mode is 0, heater will become 0. Okay. In heating mode, turn on the heater when it is too cold, but do not use the air conditioner. In cooling mode, turn the air conditioner on when it is too hot, but do not turn on the heater. Okay. Do not turn on the heater. When the heater or air conditioner are on, when heater or air conditioner are on, okay, turn on the fan to circulate the air. In addition, the user can also request the fan to turn on even if heater or air conditioner are off. Okay, so I think that's a good logic. We can submit and this will work. Okay, so we have heater, air conditioner, fan on. Okay, mode. Okay, good. Yeah, as usual, because it's a very easy problem. We can also try to combine these two. We can say that okay, heater comma air conditioner when mode equal to 1, check if too cold is 1, then return this, otherwise return this. If mode equal to 0, then if too hot is 1, return this, otherwise return this. So what we can do is we can say assign heater comma air conditioner equal to mode. So if mode is 1, if mode is 1, okay, if mode is 1, we check if it is too cold or not. Too cold? If yes, turn on the heater. If it is too cold, turn on the heater. Okay, 2 tick B 10. I don't remember to write B. Okay, so if mode is 1, check if it is too cold, return 2 tick B 10. Okay, otherwise, I could have used shortcut as well. Okay, I'll show you one shortcut. What I will do is I'll just remove all these things. Okay, so when mode is 1 and too cold is 1, okay, then heater becomes 1. So I don't need to return this. I can just uh, but anyway, I'll just write this logic, then I'll show you that. So I'll say that when mode is 1, so it's like heating mode. So I say if it is too cold, okay, return 10. So it's like heater 1, conditioner 0. Otherwise return to tick B 00. Okay. Okay. Otherwise, if the mode is 0, then I check for similar thing. Okay. It is too hot. If it is too hot, I return 01, which is like not heater and air conditioner, or we return 00. So this is one thing we would like to try. Okay. This should also work because I'll check the mode first. If mode is 1, it is in heating mode. So it is too cold means turn on the heater, turn off the air conditioner, or turn off both heater and air conditioner. Otherwise, if mode is 0, It is in cooling mode. So I check it is too hot. Turn off the heater and turn on the air conditioner, or turn off both the heater and air conditioner because it's not too hot. Okay, so I submit this and see it's running. Let me see what it returns. Okay, so yeah, it's a success. Okay, can I make it better? Mm, at least I'll just remove this for now. Okay, and now I'll show you. Heater means if mode is 1 and too cold is 1, heater gets 1. Okay, otherwise it gets 0. So I'll just remove this condition. And also, if mode is 0 and too hot is 1, then also output returns 1. If mode is 0 and too hot is 1, then air conditioner becomes 1. Okay, so let me try this out. And one more thing I forgot actually. Here also we can just return this. I don't need a. It's like if heater is there or air conditioner is there or fan on is requested, the fan will turn on. So I return this and it's running. Okay, it's a success. It's a very simple code now. Okay. Okay. So the previous problem can also be done in this way. I never thought that way in the previous problem, but it can also be done this way. Okay. So I hope you understood the solution. If you want to, revisit the previous ways I solved this problem, you can just rewind, or rewatch the solution, pause it, and try to understand. Okay. So yeah, let's move on to the next problem. Okay. So it says there's a population count circuit which counts the number of ones in an input vector. So there'll be an input vector, big vector, and the circuit counts the number of ones in that input vector. Build a population count circuit for a 3-bit input vector. Build a population count circuit for a 3-bit input vector. Okay. Counts the number of ones in an input vector. We did this kind of a problem before. Counts the number of ones in an input vector. Build a population count circuit for a 3-bit input vector. So this is a 3 input like 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0. This kind of input will come, and we have to calculate how many ones are there in the input vector. Okay. So what we can do is we can just say, okay, because this is a very easy problem here because it's a 3-bit vector, we can just add them up. We don't need a for loop and all for this. Previously we used a for loop. What we did, we added each and every bit from starting to the end. We added every bit and then found out the value of output. So what we will do here is a very shortcut kind of thing, because dependent on this problem. So this is an easy problem. So we will do a shortcut. Maybe before that, I'll try to solve this in the formal way. Okay, let's solve it in the formal way. So we'll say always at the rate start begin end. Okay, what we will do is we will say for int I equal to 0. Okay, I'm writing everything wrong seems. For, for int I equal to 0, I less than 3, I equal to I plus 1. So this is the formal way to do it. Okay, and what we will do here is a begin end. And then we will write out equal to we will write out. We'll say int uh, count once. Okay, or we can just say count once. Okay, and then because integer it starts with 0, so we will say count once equal to count once plus in of I. So from 0, 1, 2. Okay, so each and every bit we will count and add. Basically, if in of I is 1, we will add it. If in of I is 0, we will add 0, so it doesn't change. Okay, and then what we will do is after this always block or before this always block, we will say assign out equal to, okay, count once. Okay, we'll say assign out equal to count once. Here what I'm doing is for int I equal to 0, I less than 3, I equal to I plus 1. So 0, 1, 2. Count once equal to count once plus in of I. So it count the number of ones. So yeah, that's pretty much it. Uh, let me submit. It should work. Hmm. Assign 1 or 0 equal to 1 instead of assign 2 tick D1. Okay. Seems like whenever they are giving the input, immediately they are checking the output even before the calculation is done. So that's where the output is mismatching. When I give 1, I get 1. Okay. When I give 2, okay. Another thing is there. Okay. Another mistake is there actually. Count of ones should be reset. Count of ones equal to 0. 1 tick B0. So that reset I need to do, which I didn't do. If I do count of ones equal to 1 tick B0, because it's an integer, I have to reset it to 0. Sorry, I should not do that. I should actually do 0 because it's a 32-bit integer. Now I need to do addition and then give. Now it should actually work. I got it. Previously we were not resetting the value of count. Now it should work. See, it's a success. Okay. So we are getting my output is matching the reference output. Okay. Now there's a shortcut way to do this. The shortcut way is just say out equal to in of 1, basically doing the same thing. Okay. And this is assign out equal to in of 1 plus in of 2 plus in of 0. Okay. So what I'm doing is out equal to, I am adding all the 3. So it's like if it is 0, it doesn't add. I mean, it adds 0, nothing changes. If it is 1, it adds 1. If this is 1, it adds 1. So it's like 2 ones are there. Okay. So this is another way to solve this problem. Okay. See, it's also a success. Okay. So yeah, let's move on to the next problem. This is pretty simple. Previous solution to this problem is a bit lengthy, which is not needed in this case. Okay. So yeah, let's move on to the next one. It says get SV. Okay, so what is get SV? We are given a 4-bit input vector, input 3 down to 0. You are given a 4-bit input vector. We want to know some relationships between each bit and its neighbor. We are given a 4-bit input vector. We want to know some relationship between each bit and its neighbor. Out both. So each bit of this output vector should indicate whether both the corresponding and its neighbor to the left are 1, for example. Okay. Let me take a break. We will cover this in the next video. Okay. So that's all for this video. Okay. I hope you like this walkthrough series. You are liking this walkthrough series. Okay. So if you have approached the problem differently, if you have a better approach, or if you have some doubts, in any case, please do let us know. If you have a better approach, please do drop that better approach, your approach, uh, in the comment section. Even if you have a different kind of approach, a new approach, uh, even if it looks different, just drop it down in the comment section. People will learn new ways of solving these problems basically. And if you have any doubts, small or big, uh, don't feel shy. Please ask. Okay. I'll reply in the comment section. And if it's a big lengthy doubt, which I can't explain in the comment section, I'll create a separate video for it. That being said, try to solve these problems uh, without watching the walkthrough first, and then watch the walkthrough to learn how I am solving it. Because many of these problems I am solving in multiple ways. Okay. And also feel free to like, share, and subscribe this channel, and let others know about it. Your friends or whoever is practicing, HDL bits. You can just send these video series to them. it will be a great help for them as well. And if you want, you can support. We will, try to give you something, maybe some UPI ID or something. You can support in that. So each and every support, each and every small contribution will help me to become a bit more, basically independent on the things I am currently doing. So basically, I can focus a bit more on creating good videos like this. Okay, good walkthroughs like this. Okay, so yeah, any contribution is uh, very much appreciated, very much appreciated. So I'll share you uh, the ways you can reach me out and the ways you can contribute. Okay, so thank you all. Uh, we will start with this problem in the next class. Okay, thank you. Bye.